material today because it's a lot of stuff and I want you to have time to work on your activities. So we're on schedule, unfortunately. I mean, good for us, but unfortunately my other class is a class behind. But today we're going to cover modeling with exponential functions. So you'll see why we have to solve exponential function. You'll see some of the uses for exponential functions. On Monday, we're going to look at how log equations and log functions are used and how to solve those. We already know. Then on Wednesday, you'll get your last take-home quiz, and that will be due on Monday. Remember, you can turn in this project anytime. You do not have to wait till the last day. Someone from my first class just turned it in. I've graded it. She'll get it back on Monday, and she'll have everything she needs. So I did give out the projects. If you don't have it, I have a couple up here you can get at the end of the semester. It's on a green sheet. Okay, so let's take a look at today's preview activity. Let's do it together. I'll give it to you afterwards, Claudia. So let's take a look at this. This is a scatter plot. Those of you who are into video games, do you know the video Call of Duty? Okay. All right, I don't know anything about it. So this shows a scatter plot beginning in the year 2004 through 2010 of the retail sales of the Call of Duty video game. And so we're going to be working more on this next Wednesday. But I'm curious, if you saw a scatter plot like this, and we were going to throw the data into either GeoGebra or our graphing calculator and do a regression, would you be asking the calculator or GeoGebra to fit a log function, an exponential function, or a linear function to this data? What do you think you would use? Yeah? Exponential. You would use exponential. And why is that?
Because of the curve right there. You can see a little bit of a curve.
Well, it's not just that it's a curve. What if the curve went like this? So what is it about the curve? Can you? It
goes in an up. It goes in an upward horizontal direct.
Upward horizontal. I don't know how you do upward horizontal.
Like this.
I see like that. Yeah. Okay. But what is it that you would say that it's like that versus just say putting a line through it like that? I mean, I could probably get a line that fits that pretty well, right? Probably. So.
It's because that fits the line a lot better.
You think it fits better? Do you think you could find a line that goes through that pretty closely and it would be a pretty good estimate? Okay. And in fact, let me just show you. Here's GeoGebra. Here's your exponential function. And here's your linear function. And they both fit fairly close. And in fact, I put it into my graphing calculator while my other class was doing their class activities. You can see that both of these, either the linear function or your exponential function, is a very good fit in both situations. So that's where our statistic called R-square comes in. If you form a regression, a linear regression, here's the value for the slope, here's our y-intercept, R-square, because we need R-square now because we're comparing things other than straight lines. R-square is 0.93. That's pretty close to 1. It's a pretty darn good fit. With our exponential function with 65.7 and b being 1.6178, say, raised to the x, that would be the exponential function that this exponential regression gives me. And look at R-square here. R-square here is 0.98. So both of them are very good fits. However, the exponential is just a little bit better. So this is the type of thing you're going to be looking at on Wednesday. You're going to be seeing a scatter plot. You're going to be trying to fit some type of function to the data, and you'll be looking on your calculator to find the R-square value to see what would be the best model. Okay, so let's come back now to exponential and growth and exponential decay functions and see how we use them. So we've been working with functions that pretty much look like this. Either our parent type of exponential function or a function that might be transformed in some way with a value outside of b to the t. So this is like with our graphing in our equations, we've been working with functions that look like this. Once we turn them into applications and there's stories behind them and real kind of data in a real situation, we start to be a little more explicit. Instead of calling things like baby A, we might say, well, the initial thing we're looking at is a population, or the initial thing we're looking at is the number of people with a particular virus, or the initial thing we're looking at is the number of bacteria in a petri dish. I mean, there's so many applications. The number of milligrams of a drug in your system that has a half-life, and you want to find out how long it's going to take for that drug to reach a certain level. So there's all types of questions you can ask. So clearly this first equation here looks a lot like what we've been used to seeing, little a times b to the t. The only difference is now I call it a sub naught because it means the initial amount. Okay, that's all that means is the initial amount, which is when time is 0, how much do you have? It's your initial amount, whatever the particular problem or context you're looking at, initial amount. If it was a population, you might see an equation that looks like this. P of t equals p sub naught times b to the t. You can change the variable based on whatever it is you're looking at. But they all quantity, you might say q of t equals q sub naught times b to the t. The point is here, you could look in different books and you might see different letters used to express the initial quantity or the initial amount, whatever it is. So I just want you to be familiar with looking at it that way. The big change today is, and we used to spend more time working with money and continuous compounding and stuff like that. And I had showed you earlier, let's say P of t, I showed you this PERT, this little PERT equation, which was, this is when you have continuous compounding. This would be your initial principal. This would be the rate for your investment and then the time. And since E is a constant, you could use that formula to figure out how much money you would have after investing something for a certain amount of time. So now that's continuous compounding in the bank or an investment. That's growth. That's exponential growth. So another model which is equivalent, these two equations here are equivalent. You can take this formula and you can turn it into a formula that has a base of E. When would you use one versus the other? Well, you read your application problem, and if it uses the word continuous growth or continuous decay in any part of your problem, then you're going to use this formula right here, which is base E. If they just tell you that you have a specific amount and it tells you the rate of growth, then you add 1 to the rate and you get your B value, your base value, like we found before a week and a half ago. So depending on the problem, you can use either of these two equations. So let me show you how these two equations are equivalent. They look a little scary at first, but they're really not bad at all. Probably that A sub naught. Okay. So when I say they're equivalent, I mean they're equal. So if you divide both sides by A sub naught, that goes away. And now you get B to the T equals E to the KT. Well, just a little use of parentheses right here shows you that in both of these situations, the T's are exactly the same. So B must be equal to E to the K, or E to the K must be equal to B. And that's your first statement here. If I put E to the K in for B, then I get E to the KT equals E to the KT. If I put B in for E to the K, I get B to the T equals B to the T. No surprise. Okay, but once I know B equals E to the K, and let's say I want to solve for K, I want to find this is called the continuous growth or decay rate, continuous growth or decay rate, and that's written down here for you. You don't have to write that. Okay. Then to solve this, I have to get it out of the sky, and I need to take the log of both sides. Well, this is the one situation where you definitely want to take the natural log of both sides, because look at what your base is. It's E. That's right. So the natural log of B equals the natural log of e to the k. Natural log of b, nothing's going on. There it is. It just sits there. It's just a constant. But now I get to use my log properties, and that exponent comes right down in front. Woohoo! I love this property. And the natural log of e is 1, because e raised to the 1 gives me e. So this is just 1. So there's your other equation. The continuous growth rate can always be found if you have an annual growth rate and you want to turn it into a continuous. You take the natural log of that base. So you could use one equation or the other. So let's take a look at our very first application problem here. So a couple of semesters ago, we had that really severe Ebola outbreak in West Africa. And so that day I decided to rewrite that week, whenever it was happening, I decided to rewrite the class notes using this information. I'd like to use stuff that's real if I can, right? So in that particular semester, the outbreak, when it was first detected on September 3rd, when the World Health Organization got a handle on the fact that there was about 3,900, in this case 3,902 Ebola cases in West Africa. At that point, West Africa was considered to be these 3 countries: Guinea, Liberia, and Sierra Leone. And between September 3rd and November 18th, the number of Ebola cases grew at a continuous growth rate. So the minute you see that, you think of the model with base E. So you think of this model. Okay, continuous base E. E is used over and over again from many applications that use exponential growth and decay. It's used quite a bit. So the continuous growth rate is 1.252% per day. That is K. K is our continuous growth rate. So 1.252% is equal to K, but as we know, a percentage is not a number. You have to either turn it into a fraction or a decimal. So we're going to turn it into its decimal equivalent, and there it is. Nope, that's for when it's B, Ian. Okay, remember, that's if we had base B, right? This is continuous, so our base is already determined, it's E. Okay, so let's show how we can look at both models here, and come up with the same answer. So let's go, since I want to save you a little time, I'll put both models down here. And the first model was A of t equals A sub naught times B to the t. And our second model, which uses a continuous growth rate, is A sub naught times e to the kt. Well, I'm going to work with that one first because I already know what K is. K equals 0.1252. That's my continuous growth rate, my daily growth rate, right? Continuous daily growth rate. So I sit down and I go to work and I say, okay, A sub naught. Well, this is beginning time t equals 0 is September 3rd. So A sub naught is going to be 3902. That's the number of cases I have on day 0, the first day I'm starting to record this information. So this would be like my y-intercept, right? That would be my y-intercept, 0, 3902. This being the number of days that go by, t number of days after September 3rd, and this being the number of Ebola cases. Okay. So let's see, I have 3902 times e to the 0.01252 t. So that's my function. That's my model. Here's my model, model number one. So any questions you want to ask me, I can use that model. Supposedly, I can also use the other model, but the other model has a base that I don't know. I don't know the base. I can fill in a sub naught, fine, 3902, and t is t, but I don't know the value of b. However, we just saw that k equals the natural log of b, or b equals e to the k. Remember, we just saw that, look, b is the same thing as e to the k. So since we know k, we can find b. b is equal to e to the k. Just look at the two equations and you see wherever you see the b, that takes e to the k, takes the same spot in both equations. So b is going to be e to the k. So a sub t equals 390t times e, and what was k again? 0.01252 raised to the t. And there you go. You can see how they're exactly the same. If you wanted to put in a value for b, I would suggest, anytime you do any of these problems, you want to be as accurate and precise as possible. So keep as many decimal places as you want. Notice on your graphing calculator, e to the x is the button, the little yellow function above the natural log. That's because these two are inverses of each other. And look at the button above it. Log, which is base 10, is the log base 10 of x is the inverse function for 10 to the x, the exponential. So if you ever forget their relationship to each other, it's right there on your calculator. So if I want to say e, so here's my e right there. Oops, no, natural log. Second, e to the x. So now I put in 0.01252. And if I was forced to write down some decimal approximation in here, but otherwise I would keep it just like that. I mean, it's the exact same thing. But if you wanted a decimal approximation, there it is. And again, you'd want to carry that out quite a few places so that your two answers would match. Okay, so if you notice here, look, that's pretty close, 0.01259 to the continuous growth rate. Okay, so you can use either one of these models now to answer this next question. Back in fall of 14, this class was on December 5th. So that's why I picked December 5th that day. I said if November 18th represented the 83rd day after September 3rd, how many Ebola cases would you predict for December 5th? So we figured out that December 5th represented T equals 100 days after September 3rd. And so it doesn't matter which of these models you use. Okay, so I want tables 1, 2, and 3 to use this first model right here and put T equals 100 in and come up with the number of Ebola cases. So find A of 100. And I'd like tables 4 and 5 to use the continuous growth model with T equals 100 and see what you come up with. Okay, and when each tables find their answer, check with each other, and when you agree, you can come up and tell me what you got. Regardless of which model you use, that after 100 days with a continuous growth rate of 1.252% a day, you now have almost, well, over 13,500 people with Ebola. You know, so it doesn't sound like it's a great growth rate, right? Oh, 1%, big deal. But that's quite a lot of people in 100 days. We've almost quadrupled the number of cases that we had, more than tripled. So you can't be fooled by the percentage when you're looking at exponential growth. So let's go the other way now. Let's take a look at a decay model. And the most popular decay model for exponential functions is this idea called half-life. And so you want to start us off with that, Ben T? Okay, let's just stop right there for a minute. So let's suppose I had 2,500, oh, I suppose I should, given people's mental math abilities, let's just say 200 milligrams of a substance, okay? And let's say that the half-life for this substance was 4 hours. After 4 hours, how much would I have? 100 milligrams. Another 4 hours, 50, right? Another 4 hours, 25. This is how half-life works. I wanted to remind you of that because when we were doing class 31, we had a problem very similar to that, the drug problem, where we started off with 100 milligrams. In this case, it filtered out 25% of the drug every 4 hours. So what we ended up doing, if you recall, is we said, okay, it's the rate here is 25%, and you're subtracting that from 1, and you ended up getting an exponential decay function that looks something like this. But remember what your exponent looked like. It wasn't just 4 and it wasn't just t, because each one of these are grouped by the number of hours. 4 hours makes one time period. So when t is 4 and you put a 4 in here, that's one time period. When t is 8 and you're looking at grouping hours together by every 4 hours, 8 divided by 4 is 2 time periods. So this idea of taking the time, however many days or years, and that being in the numerator, and this idea of the denominator being what constitutes, how many hours in this case, or days, does it take to make one time period. So I want you to just remember that we've already worked with this idea a little bit, but it wasn't half-life. It was just a problem about drugs. So let's come back to this model now. So I give you a whole bunch of information here that is for your you know, amusement about carbon-14. There are other dating methods now that are not carbon-14, because carbon-14 is isolated to things that are about 60,000 years old. If there's things older than that, there's other methods. And you can look that up. It's interesting. And it's really about the ratio, if I remember this right, we've got some chemists in here, it's the ratio of carbon-14 to carbon-12 in the body that we're actually looking at. But all the applications say carbon-14. Okay, so in a human being or a living plant or animal that's alive, what percent carbon do you have? 14. If you're alive, 100%, right? You have 100%. And you die 5,730 years later, what percent do you have? Oh, we haven't gotten there yet. That's the half-life. Right? You have 50%. And then another 5,730, and we look at your bones, you would have 25% of the original carbon-14 in your body. Okay, so I was going to actually go through this whole long thing to show you why we get t divided by 5730. But you know what? We really already saw that back here with the drug. Here, it was every 4 hours. With our half-life, one full half-life period is 5,730 years for carbon-14. So I'm going to save a little time and save you a little like brain cells there, and just go directly to the formula. And just like with growth, we have 2 different formulas we can use. One of them deals with continuous decay. That's base E. This is when you have a continuous decay example. And when we're dealing with half-life, look at what the base is. Half. That makes sense. If you're doubling, your base is 2. When you're dealing with half-life, your base is 1/2. So M sub naught is taking the place of our A sub naught because we're often dealing with mass when we deal with decay. So they use a little M sub naught here instead of an A sub naught. Big deal, right? Your base for a half-life problem is 1/2. And look at your exponent. Just like our drug situation, our denominator was 4 in the drug situation because our time periods were measured every 4 hours. With half-life, we're measuring how many periods of how many different half-lives have gone by. So our denominator here has to be the number of years for the half-life. So that's where that comes from. If you want to make these two equations equivalent, first notice that this particular function has the negative already built in front of r because it's a decay function. Remember, that doesn't make anything negative. It's 1 over e to the rt, right? It's just the reciprocal. Some books you will see m sub naught e to the rt. And they take care of that difference down here with this numerator. I'm just telling you this now in case you see a different book. If you see m sub naught e to the rt, then what you're going to see there instead of the natural log of 2 is you'll see the natural log of 1/2. Everything is equivalent. I just want you to know that there's several different ways you can write this. So the moral of the story is this, folks. If you have a half-life problem and you're not given a continuous rate, use the easier formula right here. Because otherwise you have to convert back and forth using these two equations here. So let's take a look. This is like a famous problem we've been using in Math 107 for quite a few years about a burial cloth for an Egyptian mummy. And someone asked me last semester which mummy. I said, I don't know, maybe it was King Tut because they unearthed part of King Tut a few years ago. So the burial cloth of an Egyptian mummy is estimated to contain 59% of the original carbon-14. So if you had 100% of the original carbon-14, and now you have 59% of it, and you're writing some kind of equation over here, do you see that the m sub naughts are just going to cancel? You got the original, whatever that original mass is, it was 100%. And now we have 59%. So to shortcut this, where you see m of t, you can just write 0.59. You could write 0.59 times m sub naught if you want. It doesn't matter because your m sub naughts are just going to become 1 when you divide both sides by it. It's totally up to you. Either way, you can write 0.59 or 0.59 m sub naught, whatever kind of floats your boat. I don't care. Then what do we have? M sub naught times what? Let's take a look again. 1/2 t. We don't know t, and we divide it by the half-life, which is 5730. So we're trying to determine how long this burial cloth has been buried when we get 59% of the original carbon-14 is found in this burial cloth. We know to make 1/2 life, it's 5730, 5,730 years. So you can see if the numerator is 5,730, 1 half-life has gone by. If it's 11,460 divided by 573, 2 half-lives have gone by. Okay, so this is how we're grouping our years into groups of 5,730. That's called the half-life. So if you try to solve this problem, the first thing you do is you divide both sides by m sub naught. So really you just wind up with this equation. You could put a 1 there for 100% to remind you what you're doing. Whoa, I love it when that happens. So you just basically fill in your model. And what's nice about this model is you always have the 1/2 as your base. That's always known. And in this case, you know your half-life. So you're really ready to go here. You've got 0.59 equals 1/2 t divided by, I have to laugh because otherwise I'd be frustrated, t divided by 5730. So what is our job? Our job is to find t. Solve for t. That's our job. Now we take the natural log of both sides or the common log, whichever one you want. Let's do the natural log. Natural log of that number, 0.59. All right, and then we get the natural log of all the crap on the other side, right? By now, you'll be able to do this in your sleep. So I want to just stop for 1 minute. I want you to take a look at that very first expression on the left side. Natural log of 0.59. If I put that into my calculator, am I going to get a positive answer or a negative? Ooh, that was fast. Remember, because our natural log looks like this, and at 1 it's 0, so any number between 0 and 1 is below the x-axis, right? So this will be negative. And when you end up dividing it by this one, natural log of 1/2, that's always also negative. So a negative divided by a negative will give you a positive. Just wanted to keep reiterating, like just kind of keeping that graph of a logarithm in your head. All right, so again, we're not ready to do much. We're just going to keep playing with this equation. But the nice thing right now is we get to use our power property for logs. That's going to bring that log from the sky down to the earth. We're going to ground this thing. It's going to come right down in front. T divided by 5730 times the natural log of 1/2. So you could put that fraction bar all the way across if you want. That looks to me like 3t divided by 5. That's what it looks like to me. It's just some number multiplying t divided by another number. It's a fraction. The natural log of 1/2 divided by 5730, that's your coefficient. So depending on your algebraic skills, you can do this in one step by multiplying both sides by the reciprocal of this, or you can first multiply both sides by 5,730 if you want, and then divide by the natural log of 1/2. It's up to you. So regardless of which way you do it, you're going to end up multiplying both sides of that equation by 5730. And then when you do that, you'll have the natural log of 1/2 multiplying t. So then you'll divide both sides by natural log of 1/2. And there's your answer for t. So let's see how many years this is. Could we have kind of estimated this? Yeah, we could have, because look, we have 100% carbon-14, and after 5,730 years, we're going to have 50%. And right now we're at 59%. So we know our answer has to be less than 5,730. I don't know if it's closer to 5,000 or 4,000 or 4,500 years, but I know it's less than 5730, and it's got to be somewhere between 4,000 and 5,000, I'm estimating. Okay, so let's see what our calculator gives us when we do this. We take out our calculator and close it and then open it. Our calculator, and again, be careful with your parentheses. Since my calculator knows order of operations, I can do this numerator without having to use any extra parentheses times the natural log of 0.59. My calculator knows to do, why did that, did they give me a separate, okay. Oh, okay, let me just clear this. 5730 times the natural log of 0.59, okay. So I don't have to do like a whole set of parentheses around the whole thing, because the calculator knows I'm going to do that multiplication before I divide by the natural log of 1/2, which is 0.5. And there I go. 4,361 and about 3/4 years. So if I were writing this on a test, I'd say t is approximately, that's those squiggly lines, 4361.75. And then if I write my sentence, that's when I put in my unit years. T T doesn't have the years after it. T is just a number. So this is the exact answer. This is the approximate number of years. Every single half-life problem that you do that doesn't use E as a base will always have this in the denominator. Always. It will always have the natural log of 0.5 because look at what you have on your right side. You have the natural log of a half raised to whatever your exponent is. That exponent's going to come down in front. So the natural log of 1/2 has to be divided. Both sides have to be divided by that to solve for t. So you will always have the natural log of a half in the denominator when you solve these problems. Any questions on doing this problem right here? Now, this is where I say, don't make life hard for yourself. Why in the heck would you use this formula? You could, but you have to solve for R. You don't know the continuous decay rate here. So you'd have to take the natural log of 2 and divide it by 5730 and put that in where you see R. It's possible you'll get exactly the same answer. And if you're a bit of a masochist, go ahead, do it. It's fun. You know, you'll have pain. No, I'm only kidding. You know, you can do it. But you don't want to use these messier half-life formulas if you don't need to use them. But you can go back and forth just like I showed you with the other one. Okay, so this is my really big hint for the final exam. Final exam, put on that your first class activity. And on this class demo where you see something called logistic growth, put final exam. You will see a logistic growth function on your final exam. It might even be on the last page of the final exam. I don't quite remember. But you will see this and you will have to work with it. But you'll also have a really nice looking graph to help you alongside of it. But logistic growth really is, things don't grow exponentially forever. It can't, because there are limited resources in the world, whether it's space, or whether it's food, or whether it's food and space and water. You eventually have a limit to your growth, regardless of what kind of growth you're talking about. Okay, so this model, logistic growth, is really a more accurate model to be working with. And if you looked at this curve, does it look like a particular letter that you're familiar with? Does it have a particular S? Yeah, it's S-shaped. We say a logistic growth is S-shaped. A real fancy word for S-shaped, if you want to impress your friends at your next cocktail party, is sigmoidal. Sigmoidal. I love that. My affine and projective geometry teacher in college, it's a different geometry than Euclidean, which is what you learn in high school. She used to always say this. You can impress, your friends at your next cocktail party. And I just imagine, yeah, this person, these math people probably went to cocktail parties, right? We didn't go to cocktail parties in the early 70s, I'll tell you that. But anyway, and they probably talked math. Well, I love that line. I always thought it was funny. So you guys didn't laugh, but anyway, I just wanted you to know that it has a little bit of a background, the cocktail party. All right, so it's S-shaped. So if you look at this blue part of the curve right here, this blue part, which you can see the blue better on my screen than you can on your, if I just looked at that blue part, what kind of shape does it have? Exponential, right? It has an exponential shape because as with anything that grows, it starts off very rapidly here. And so it does have that exponential increase, that look. But then the growth rate is starting to slow down and it's starting to get slow. It's still increasing. This is always increasing, this type of function over the whole domain. But look, it's slowing, the rate is slowing down, and look what it's approaching, a horizontal asymptote right here. And that's like your ceiling. You can't get beyond that growth, that number. That horizontal asymptote actually has an equation. Remember, horizontal asymptote, some of you got this wrong on your test, is y equals, right? All your y values are the same, y equals c. Notice where C appears in your model. It's the numerator. That's called the carrying capacity. If you take an environmental science course, you'll hear that term, carrying capacity.
Overpopulation.
Yeah. It's like certain areas carrying capacity. Think about how much can I carry? How much can planet Earth? That's a closed environment. What is the carrying capacity for planet Earth? If you go down to the library and you get out some books, you can get out multiple books about the carrying capacity of the Earth, and you will get a huge spread on what people think is the carrying capacity of the Earth, because nobody really can figure it out. Okay, but there's a limit to population growth. So if I asked you what the maximum growth level is, all you have to do is look at C here. And if you think about this a little bit, e to the negative bt, that really means 1 over e to the bt, and time is going on here. You're looking at your end behavior. This, as t gets really big, this approaches 0. This whole term right here. So you get c divided by 1. So that's why the long-term behavior of this function is that numerator, the carrying capacity, C. And we use a big C to help you remember that it's the carrying capacity. Other things we notice about this, yep. No, that's it. I don't know anything about here. Out here.
Yeah, but
Okay. So the other thing I just wanted to point out for those of you going on to take calculus, that point right there is called an inflection point. And you'll find in calculus how to calculate the value of that point. And that's where this curve goes from an increasing growth rate to a decreasing growth rate. That's called concave up becomes concave down at that inflection point. But again, that's all calculus. Some of you will see that later, some of you won't, depending on what calculus you take after this. So let's play with this model a little bit. It's a fun model to work with. It looks a little scary because of all the, oh, didn't I give you a problem? Didn't I give you another problem? I didn't. No, we could use it, but then I'll take all the fun away. Let me just start you off. So look, you look at that and you get a little bit of like a pang in your stomach because it looks complicated. But you know all of this. You know what it means to divide. You know what it means to add in the denominator. You know what E is on your calculator. And then you just have this exponent. So if someone comes along and gives you a value for T, like this is a model, this is right out of your book, the spread of a flu. And I ask you, let's do the first one. How many people became ill with the flu when we first started recording the number of cases in the epidemic? So that's the initial value. How do I find the initial number of people? What do I put in for T? 0. So you could look, let's say, here's your graph, and on your final, you'll have a graph with grids, and you'll be able to read most of your answers right off the graph. But so if I had a little better picture for you, it would be that value right there, my y-intercept. But I can find my y-intercept because I know that to find my y-intercept, T is 0. So yeah, 30,000 divided by 1 plus 20, e to the negative 1.5 times 0. Yep. And what's e to the 0? Yep. So anything to the 0 power except for the number 0 itself is 1. And we get 30,000 divided by 1 plus 20 times 1, which is 30,000 divided by 21. So I throw that in my calculator. See, it looks scary, but it's not scary at all. It just is, let's see, 30,000 divided by 21. And so I'd probably tell you to round it to like the nearest tenth of a day. So this is approximately 1428.6 days. Right? Is it days or hours, I wonder? I didn't put that in, did I? No, it must be days, yep. So that's how you work with this, okay? It looks a little scary, but it really isn't bad, and just work through your class activities. I do want to point out one thing about your class